Hi everyone, this is Professor M. Science, and today we want to answer the question, what happens after a quantum measurement? This is another one of our videos on rigorous quantum mechanics. What happens after you measure a physical property of a particle is one of the weirdest things in quantum mechanics. To understand it, we're going to focus on a particular example. What happens after you measure the position of a particle in an infinite square well? Using the infinite square well as an example has the advantage that the maths is very simple, so you can see with your own eyes where the physics comes from. I have also prepared some animations along the way, so this will be a very visual and interactive video. In fact, you will be able to modify the animations yourselves and play around with the time dependence of a particle in a box by checking my Jupyter notebook linked in the description. Also, if you haven't seen the video yet on the basics of the infinite square well potential, check it out. Otherwise, let's go! The dynamics of a quantum system is governed by the Schrödinger equation. This equation, which features in postulate 6 of quantum mechanics, plays the same role that Newton's second law plays in the case of classical mechanics. What I have here is the one-dimensional Schrödinger equation written in the position representation. When the potential is time-independent, then the dynamics of the system takes a particularly simple form, and this is what I want to explore in this video. For full details about how this works, check the video on the Schrödinger equation. What I will do here is I will summarize the main results that will allow us to study the dynamics of a specific system. To study the dynamics of the system, we have to start at the beginning. What does the system look like at time equals 0? We write the wave function psi of x at time 0 as an expansion over the basis functions psi n of x, which in turn are obtained as the eigenstates of the Hamiltonian. In this context, the eigenvalue equation for the Hamiltonian is sometimes also known as the time-independent Schrödinger equation. In it, the psi n of x are the eigenstates of the Hamiltonian, and the En are the eigenvalues or energy levels associated with the Hamiltonian. These two ingredients are all we need in order to capture the dynamics of our system. Solving the Schrödinger equation tells us that at a later time t, the wave function psi x of t is given as again an expansion in terms of the psi n of x, and now the expansion coefficients Cn are time dependent. And their time dependence is given by Cnt equals Cn0 e to the minus I Ent over h bar. The number of terms that appear in the sum over n here depends on the initial conditions, and in the special case when the initial state is an eigenstate of the Hamiltonian, then only a single term appears in this sum. In that case, the time dependence becomes trivial, and we call those stationary states. To see why the time dependence is trivial in this case, we consider the wave function psi x of t with a single term j in the expansion, and the time dependence is as shown here. And we know that the relevant information about our system is given by the absolute value squared of the wave function, and when we calculate that, we see that the exponential term that captures the time dependence goes away. The result is that we end up with a wave function whose absolute value squared is time independent, and that's why this is called a stationary state. This result also highlights the fact that multiplying our wave function by a global phase does not change the physics, because this global phase always goes away when we take the absolute value squared. What I want to tell you about in this video is what happens when there is more than one term in this sum. In that case, the dynamics becomes much more interesting. To do that, we only have to follow the following recipe. First, we have to solve the eigenvalue equation for the Hamiltonian to find the energy eigenstates and energy eigenvalues. Second, we have to expand the initial state of our system in the basis formed by the eigenstate of the Hamiltonian. And third, we have to construct the state of our system at a later time t simply by building the time dependence of the expansion coefficients by using the eigenvalues of the Hamiltonian. The example I will use in the rest of the video is that of the infinite square well potential. This is a system that we can solve analytically, and in fact we have already solved the eigenvalue equation for this system. Check out the video in the description. All we have to do moving forward then is to do points 2 and points 3 here to understand the dynamics of the system. As a reminder, when we solved the eigenvalue equation for the infinite square well potential, we found that the energy eigenvalues were quantized. E of n was proportional to n squared, where n could only take integer values. The associated wave functions psi n of x had definite parity, because the infinite square well potential is symmetric with respect to a reflection about the center of the well. As such, they were proportional to the cosine for odd n and proportional to the sine for even n. To study the dynamics of a quantum system, we're going to start with the simplest possible extension to stationary states, which is the time evolution of a superposition of two energy eigenstates. To do that, we write our initial wave function psi x0 as an equal superposition over psi j and psi k. In this case, the expansion coefficients cj0 and ck0 are equal to each other and equal to 1 over square root of 2. We choose 1 over square root of 2 to make sure that the wave function is normalized. The wave function at a later time t is now simply psi x of t is equal to 1 over square root of 2 psi j of x e to the minus I ej t over h bar plus psi k of x e to the minus I ekt over h bar. Remembering that all we care about is the absolute value squared of the wave function, we can multiply our wave function by a global phase, e to the I ejt over h bar, and this gives us a very convenient expression for the wave function where the time dependence is only in the psi k term. Calculating the absolute value squared of the wave function now gives us this expression here, which has 4 terms. The first 2 terms are time independent, and it is the cross terms that capture the time dependence. If we look at the wave function psi n of x at the top, we see that it is in fact a real wave function. That means that the stars in the cross terms are irrelevant. This means that we can combine the cross terms into a single expression that depends on a cosine function. This cosine function captures all the time dependence of our system, and the frequency at which the cosine oscillates is given by the energy difference between the 2 eigenstates that are included in the sum. This last term is called the mixing term, and is the one that allows us to have more interesting dynamics beyond those of the stationary states. To study a concrete example, I'm going to look at the case when j equals 1 and k equals 2. The first term is time independent. It corresponds to the ground state wave function of our system, which we can draw here, and its absolute value squared is given by this. The second term is again time independent. It corresponds to the first excited state wave function, and again we can draw its absolute value squared. The third term is the one that's interesting from a time dependence point of view. If we start with psi1 times psi2, we just have to multiply the 2 wave functions we've already drawn, and we obtain this green curve here. And then this term captures the time dependence through the cosine function, which oscillates at a frequency omega, which is equal in this case to e2 minus e1 over h bar. To build the absolute value squared of the total wave function, we need to add these 3 terms, and we obtain the red curve here at time equals 0. The green curve will oscillate due to the cosine term with a period 2 pi over omega, which in this case is 2 pi h bar over e2 minus e1. And for example, we can ask what happens at a time which is half that period. At that point in time, we obtain cosine of pi, which is minus 1, so the green curve is multiplied by minus 1, and we obtain that the total wave function squared is given by this dashed curve here. We can see that the high peak on the right-hand side of the well has decreased in size, whereas the small peak on the left-hand side of the well has increased in size. If we consider smooth changes in time, we'll see that the peaks oscillate at a frequency omega. It is quite instructive to see how this works in some more detail, so I have implemented the dynamics of this system in a Jupyter notebook, and you can find the link in the description and you can play with it yourself. What I'm showing here are 2 examples of the output of that code, and the one on the left corresponds to j equals 1, k equals 2, the case we were just discussing. The frequency of oscillation omega is proportional to the energy difference between the 2 states that we are mixing, and in this case it corresponds to the energy difference between E2 and E1. And this is what the dynamics of the system looks like. We see that the high probability of finding the particle on either side of the well oscillates periodically in time. The case on the right corresponds to j equals 1, k equals 20. The k equals 20 energy level has many more peaks, and this is why the initial wave function looks like it does. The frequency is still proportional to the energy difference between the 2 states that we're mixing, and we realize that the energy difference on the left-hand side is much smaller than the energy difference on the right-hand side. That implies that the frequency of oscillation will be much larger on the right-hand side than on the left-hand side, as we can very clearly see. Again, have a play yourself with the Jupyter notebook to see what happens when you mix different energy levels. Now that we understand the dynamics of a system that mixes 2 energy levels, we're ready to tackle the much more general problem of what happens when we have a general mixture of energy levels. To do that, we're going to look at the concrete example of the time evolution of a system after a position measurement. A position measurement collapses the wave function to a single point in space where the particle is measured to be. We can therefore write the initial wave function, psi x0, as the delta function centered on x0, where x0 is where the particle is measured to be. Here I must make a subtle but important point, which is the fact that the delta function is not normalizable. The delta function is not a square integrable wave function, and therefore it doesn't belong to the Hilbert space of valid wave functions. So what does it really mean when we say that we measure the particle to be at x0? What we mean is that the particle is in a very small region in space centered at x0. We write the corresponding function as capital delta x minus x0, which is a function that peaks at x0, but it has a finite width. This makes this function normalizable, and therefore it's a proper wave function in our Hilbert space. In this language, the delta function represents a limit of the capital delta function that we can get arbitrarily close to but never quite reach. To simplify the maths in what follows, I will in the first instance use the delta function, and then we'll construct the capital delta function to do the proper physics. As always, we start by applying the initial conditions, so we write psi x of 0 as an expansion over the basis functions psi n of x, and to calculate the expansion coefficient Cn of 0, we need to calculate the overlap between the wave function and the basis functions. Remembering that the wave function is simply the delta function, then the calculation of the integral is very simple and we obtain psi n of x0. We now construct our wave function at a later time t in the usual manner by having the time dependent in the exponentials, and this term here corresponds to the time dependent Cnt. We can replace now the expression we found above for Cn0, and we obtain this expression here. It is important to note that the psi n x0 in this case is a constant, because this is the function evaluated at the specific point x0, whereas the psi n of x here is a function of x. The psi n of x functions are sines and cosines, so how can we combine them to give us a delta function? What's going on here is that these are precisely the expansion coefficients that lead to destructive interference between the sine and cosine terms absolutely everywhere in space apart from the x0 point where they lead to constructive interference. Now that we have a mathematical expression for psi x of t, we want to understand what this means physically. At time equals 0, the initial wave function was a delta function, and we can draw a delta function inside the well. However, we remember that this was not a valid wave function, instead we had the capital delta function, which is a function that is still centered on x0 but now has some width around x0. From a numerical point of view, all we have to do in the solution above is to truncate the sum over n to some finite number of terms, and then we obtain an approximation to the delta function that gives us a capital delta function that is a properly normalizable wave function that therefore belongs to our Hilbert space. The reason why we obtain a finite width when we truncate the sum is because by neglecting some terms, we now no longer have the destructive interference that we had when we obtained the pure delta function. To understand what happens at a later time t1, we note that each basis function psi of n oscillates at a different frequency omega n equals en over h bar. Because each basis function oscillates at a different frequency, then this will break further the destructive interference that led to the very localized wave function that we started with, and this means that the overall wave function will spread. At much later times, the coherence that we had at the beginning to localize the state at a single point will be completely destroyed, and the wave function will be completely flat, and the particle could be anywhere in the well. To finish, I want to show you another simulation of the dynamics of this system, and again you can play with it yourself by following the link in the description. What I'm showing here is the initial wave function centered at x0, truncated at 100 terms in the expansion above, and you can see that indeed it is very much localized around x0, but it still has some finite width. We can therefore write it as delta x minus x0. We can now look at the evolution of a quantum particle right after a measurement, and we can see that initially this very narrow distribution starts spreading around that point. It first hits a wall, it then hits the other wall, and eventually the distribution looks completely flat, very different to the one we started with. Having seen this, it is instructive to compare the classical case to the quantum case of measuring a particle and seeing how it evolves in time afterwards. At time 0, when we measure the particle, in the classical case we know that the particle is exactly at x0. In the quantum case we know it is around x0. At later times, in the classical case, Newton's laws tell us exactly what the position of the particle will be. In the quantum case, the time evolution is governed by the Schrödinger equation, and all it tells us is what the wave function will be at a later time. But all the wave function is telling us is what is the probability of finding the particle at any given point when we measure it again. In the example we have here on the left, you can see that the probability at a late time is pretty much all over the well, so we can draw this horizontal line telling us that the probability is essentially uniform within the well, so the particle could be anywhere within the well when we next measure it. Well, I hope this video blew your mind just like it does to me every time I revisit this problem. What we have seen is that quantum particles behave in very different ways to classical particles, And this really provides almost infinite possibilities for quantum theory. You can check many of those in my other videos. If you like this video, or if you'd like to send me suggestions for future videos, please subscribe.